Hear me? Hello. Well, welcome everybody again for our new event of the De La Pietra lectures. Many of you know probably that the De La Pietra families are funding this series of lectures. They are actually very good friends and benefactors of the Simon Center and science in the community. So we're really grateful that they allow us to have this privilege of hosting people like Adam Riess and many other prestigious lecturers that came in the past and hopefully will come in the future. So. Anyway, today we have Adam Riess, which is a real privilege. He's one of these people like Prometheus who stole the fire from the suns, and then that has cast a spell on all of us, because the discovery that they made about the fact that the universe is accelerating, the Cosmodrome Constant, dark energy, is something that is really making people really not sleep to understand what's going on and how things happen and so on. Now, if you look at his webpage, he has an enormous number of more than merited accolades and prizes and so on. So rather than bother you and bore you with all these descriptions, I would like to let him present his subject, Supernova Reveal an Accelerating Universe. Adam.
Okay. Can everybody hear me okay? I think so. I want to thank the De La Pietras for inviting me to give this lecture. Very honored. I see a lot of people in the audience. I saw them earlier drinking wine, and I've always wanted to do this experiment of, I have a hypothesis that people will enjoy my talk more if they drink more wine. So we have a questionnaire at the end of the talk where you're going to fill in what you drank and how you felt about it. So that'll be interesting. Okay, so let's get started. So I'm going to tell you the story of how observations of exploding stars revealed to us that we live in a universe that is not just expanding, that we already knew, but that it's expanding faster and faster. That is, it's accelerating, propelled by a mysterious new component of the universe that we call dark energy. Before I can tell you about the exciting parts of this discovery, let me give you a little bit of background, a sort of crash course in cosmology, so that you can appreciate the discovery later on. This is a deep view of the universe. This is actually the deepest view ever taken of the universe. The way you take a deep view is you pick a pretty ordinary patch of sky and you use a powerful telescope, in this case the Hubble Space Telescope, and just like any photographer knows, if you want to observe faint light, you have to keep the shutter open a long time. So we kept the shutter open for about a month, staring at this blank spot, and what you eventually see rising are the very faint distant galaxies. So there are tens of thousands of galaxies in this picture, the faintest of which are 1 trillion times fainter than anything you could see with your naked eye. And this is just a tiny patch of the universe. If you took a single grain of sand and you held it out at arm's length, you would cover a patch this size. So obviously the universe is very big. Now, when you look at a picture like this, you notice that although I said we kept the shutter open for many months, the galaxies don't appear to have smeared. They don't seem to be racing across these images. So the universe looks static to us when we look at that, but that's really a false impression. In reality, the universe acts like it received a big kick we call the Big Bang, and now the separation between galaxies is growing. You could think of the universe like a giant loaf of raisin bread rising in the oven. The galaxies are like raisins. We sit on some raisin, we look at the other ones around us, they're moving away from us. We understand no matter which raisin you sat on, everything would be moving away. The further away something is, the faster it moves, because there's more dough or space between us and it. So you might wonder, how is it that we really know the universe is expanding? And the answer is, yeah, we checked. We've checked all the results in this talk, but in particular, this is something that we've really focused on checking. So how is it that we would check this amazing fact? Well, if you remember that animation that I showed you, the key is to be able to measure how far away those galaxies are and how fast they are rushing away from us. So observers like myself spend a lot of time focused on making measurements like that. So let me tell you how it is that we measure how far away those galaxies are. And to do that, I'm going to remind you, how do we measure how far away anything really is even on Earth? So on Earth, we have a whole lot of different tools for measuring distances. One of those is called parallax. You see a crew of surveyors out on a road, and they may be sighting some distant tree they would like to know the distance to, but they don't want to swim across that stream. So they sight that tree relative to maybe something like a distant mountain, and then they move their gear along some baseline they know the length of and see how the angle has changed between the tree and some distant mountain. That is, they create a triangle in space, and they measure distances that way. This requires a very long baseline if you were to apply this in the universe. Another method that we use is the method of lighthouses. So a ship captain at night is trying to make sure he's very far from shore, and so he knows a lighthouse is intrinsically very luminous. So he or she is hoping to see it appear very faint to tell them that they're still very far from shore. Now, they could get fooled if it was a foggy night. Then that I'm not going to take this call now. I'm really not. My watch doesn't want to. My watch wants me to, but I don't. All right. So the lighthouse could be a foggy night, and then it would look very faint and fool you into thinking it's far away when you're really close to it. But we have other objects like foghorns. A similar kind of concept, that it is something that is intrinsically very powerful, in this case in sound, that cuts through the fog. And so in that case, you're listening for something to be very faint, to be very far away. And then a last method I call objects of known size. So we do this every day. We look out and we see objects, we recognize their physical size, but they appear small and allows us to gauge their distance. So when we look at this squadron of airplanes here, we can see these very small versions. We assume those are just the same thing, but just further in the back. It's not like these are baby airplanes, that came from this family of airplanes. These are actually much further back. And so we have all these tools. We don't have any of these exactly in this form in space, but in space instead we have telescopes, and we have what nature provides. And nature provides a number of sort of analogs to these. So I'm going to talk about an analog of the lighthouses, which astronomers call standard candles. Standard candle in our speak is anything whose luminosity you understand well, so that when you see it far away and it's looking faint, you can measure how far away it is from its brightness. And so here is a galaxy that may have 100 billion stars in it, and at some point in its life, one of those stars may explode. We'll show you what that looks like here. And when it does that, because we recognize the true luminosity of that kind of supernova explosion, we can tell how far away from its brightness. It's just a basic application of the inverse square law, that the brightness declines as 1 over the distance squared. So you could just think of this as, if it's twice as far away, it's 4 times as faint. If it's 3 times as far away, it's 9 times as faint. So astronomers go out and look for standard candles like an exploding supernova in order to gauge distances. So that was the first part of that animation. The other part, of course, was the fact that it looked like everything was rushing away from us. And the way we are able to measure this quantity is we look at actually the color of the light we are receiving from the objects we see. Now, because light is the wavelengths of the light are stretched by the expansion of space, what can start out as very blue light appears very red by the time we receive it, because longer wavelength light is redder. And so by the time we receive it, it's been what we call redshifted. This might remind you of something you learned in high school, the Doppler shift. It's a little bit different. Instead of it being due to the motion of an individual object, it is actually due to the expansion of space in between. And in fact, the fact that we see this beautiful pattern of redshifts all around us tells us that this phenomenon is occurring because of the expansion of space, not a conspiracy of all galaxies to kind of mess with us. And so when we see a standard candle, we can measure how far away it is, and we can measure how fast it appears to be moving away from us, though it's really due to the expansion of space. So returning to that animation I showed you before, instead of just appreciating it, we can actually get quantitative. We can go out and measure the distance to the galaxies around us. We can measure the speed or their redshift. They appear to be moving away from us. And by making a plot like this and seeing a linear relationship between the two, that is the signature of an expanding universe. The fact that things that are further away appear to move faster because there's more space between us and them. So if space doubles and doubles and doubles in size, further away things move faster. And if you measure the slope of this line, you are determining how fast the universe is expanding. If the universe were expanding faster, it would be a steeper slope. If it were expanding slower, it would be a shallower slope. If the universe were contracting instead of expanding, we would actually see a negative slope. This is not just a thought experiment. This was actually first determined by the astronomer Edwin Hubble in the 1920s. Actually, he was using redshift measurements made by Vesto Slipher about a decade earlier. And then on the 100-inch at Mount Wilson, Hubble measured the distances and generated this diagram, this plot, which, I know it doesn't look that impressive. It looks sort of like your freshman physics lab that, didn't go well. But this is actually one of the most iconic plots in all of science. I sometimes tell my students I don't have a tattoo, but if I got a tattoo, I would get it of this, because that's how significant this diagram was. Now, in my doctoral thesis, I continued to make these kinds of measurements, but further out. And so this was from my doctoral thesis. Edwin Hubble's whole set of measurements would fit in this tiny little red box here in the corner. And of course, as we go further and further out, we see the trend just continues. The universe is expanding. So you've learned so far that the universe is expanding, and we know how to measure that. And already we could address a really interesting question that has sort of kept people up late at night, philosophers and religious leaders and curious people, which is really, when did the universe begin? Because once we know that the universe is expanding, we can use mathematics and run the movie of the expanding universe backwards in time until everything was together. So here's how this works. Okay, here we are today, galaxies are moving apart, time is going forward, and we have measured the expansion rate of the universe, a number that today is called the Hubble constant, and it gives that present expansion rate of the universe. So now we could imagine running this movie backwards in time using the power of math to imagine the universe contracting at that same rate. So it's contracting, time is moving backwards, and let's keep running this movie until everything is on top of everything, right? That is this moment we call the Big Bang, but the amount of time it takes to run this movie backwards tells us how old the universe is approximately. Actually, it's just simply the inverse of the Hubble constant. Now, of course, this assumes that the expansion rate of the universe has not been changing over time. I'll get to that a little bit later in the talk. Now, when Edwin Hubble first measured this Hubble constant, he didn't call it that, but he got a number that was very large, and it implied that the universe was only about 2 billion years old. Now, even in 1929, people knew that was clearly wrong, that the Earth was older than that. But it's hard to measure the Hubble constant, and we've made a lot of progress over the last century. This is an article from the New York Times describing the history of just measuring the Hubble constant back in the 1920s when Hubble measured it, and how the inverse of its value tells us the age of the universe. And so there were dramatic changes as we learned more about the universe, more about the objects we were using to make the measurements. We learned that there were 2 generations of stars. That was very important. We learned to use better detectors on our telescopes. The Hubble Space Telescope was launched. And if you see this great narrowing, what was once a wide range became quite narrow. And particularly in the last 20 years or so, and particularly in the last few years, the numbers have really narrowed down as the measurements have improved. And tomorrow, I'm going to be giving a technical talk at the Simon Center on this work, on measuring the Hubble constant as precisely as we can. And that today gives a value that's better than 2% in its uncertainty, implying the universe is about 13 billion years old. Now, 13 billion is older than the oldest objects in the universe, and so we no longer have that particular worry. Okay, so you know the universe is expanding. you might wonder, what's next for the universe? You know, what happens after that? What is the fate of the universe? This is a question that has also gone way back. A useful way to think about the fate of the universe is just to think about the fate of a cannonball fired from the surface of the Earth on a mountain, let's say. This is a thought experiment that Isaac Newton famously did to try to imagine what it was like for something to orbit or to escape the Earth. And so if you fire that cannonball with greater and greater velocity, it will get further before it falls to the Earth because it's gravitationally pulled to it. If you fire it with enough velocity, what's called escape velocity, then the cannonball actually can escape the gravitational pull of the Earth. Another way to think of that is, once you fire the cannonball, if the mass is low enough of the Earth, it won't hold it back so much, and then the cannonball will escape. So it's really a question of how fast that cannonball is traveling or how massive that planet is to hold back that cannonball. So we didn't always think of it this way, though. Einstein, when he was thinking about the fate of the universe, was not imagining the universe to be in motion like our cannonball, and didn't have this question about, you know, is the cannonball going to fall back to Earth or not, because he had been given some really bad information by astronomers of his time. In 1915, when he was working on his theory of gravity, he asked astronomers, what is the universe doing? And they told him it was static. They told him it wasn't really expanding or contracting. Now, admittedly, at that time, what they called the universe was just the Milky Way galaxy, and it is true that the stars in the Milky Way galaxy don't have great velocities, and so he was told things are not really moving. And he was confused by this, because if you take some collection of objects, and they're in space and they're not moving, they're not expanding or contracting, then he thought the gravitational pull of all the objects on each other would start the process of the universe contracting. So why wasn't the universe contracting if it was static for a little while? He was puzzled, and as he puzzled through this, he came up with really what was an amazing discovery. He discovered that in his theory of gravity, although the gravity of stuff, of matter in the universe is attractive, would have that property, he discovered that the gravity of empty space itself could be repulsive. He called this property of empty space the cosmological constant. Today we would call it dark energy. And he thought, okay, if you tell me the universe is static, it must be that these two are in a perfect balance, the attractive gravity of stuff and the repulsive gravity of empty space. About 10 years later, Einstein learns from Hubble and others that the universe is expanding, that this sort of condition that he was given, that the universe was static, was wrong. In fact, famously in 1931, he actually goes and visits Hubble at Mount Wilson. Here's Hubble and here's Einstein. And I love this picture. This must be a public relations shot here, because Einstein says he has to look at the telescope to be convinced of the truthfulness of Hubble's data. Of course, in those days, even in those days, astronomers were no longer using their eyes. The objects they were looking at were so faint they had to add up the light for hours on a photographic plate. So when Einstein is looking through this, he cannot see anything that Hubble is actually looking at. But you know how embarrassing that is. So he's probably nodding along, yeah. And, it's surprising that Hubble would be smoking his pipe at the observatory, too. That's why I'm pretty sure that this is a PR shot. But anyway, some way, by looking or by how convincing Hubble was, he was convinced that the universe was expanding. So he called this, a great mistake that he had made. But this idea has kicked around for a while. So then how can we actually measure what the universe is doing? Assuming that Einstein's idea is wrong, then the gravity of everything in the universe should be slowing the expansion, just like our cannonball is decelerating. It is being pulled back to Earth. And it's really just a question of, is there enough velocity or a low enough mass for it to escape? Or will the cannonball fall back to Earth? The analogous for our universe is, will the expansion stop and the universe start contracting? Now, if we could just wait and see how the universe is evolving, what progress it's making, its trajectory, that's how we might learn it. But this would take a very, very long time. This is not a productive way. However, we have another way to address this problem. It's using this what I think of as the sort of astronomer's trick, which is instead of waiting for the future, we can just look back at the past and see what trajectory the universe has been on. And that's because I would say the universe doesn't really instant message, that all the information we get from the universe in pictures mostly is actually delayed information. So when I told you we could look at a distant standard candle and measure how fast the universe is expanding, what I failed to mention is that information is delayed. What we are actually seeing is telling us how fast the universe was expanding maybe 1 billion years ago. And so if we look at a more distant standard candle, that may be telling us how fast the universe was expanding 2 billion years ago. A more distant one, 3 billion years ago. So just by looking further and further out, we look further and further back in time, and we measure the expansion history of the universe up until the present time. And so this is a very powerful way to see if the expansion is slowing enough. It's like watching that cannonball going back and looking at, at the last 10 minutes of its flight to figure out what its likely trajectory is. Now, in the 1990s, the expectation was that either the universe resembled the model here on the left, that is a very dense universe filled with matter whose gravity was halting the expansion of the universe, and that expansion would stop, and then the universe would start to contract again and come together and end in kind of a big crunch, the opposite of the Big Bang. And cosmologists characterize that kind of universe as having matter density greater than 1, omega matter greater than 1. That's like for the cannonball, being on a very heavy planet, it will certainly succeed in pulling the cannonball back. The other possibility is a very lightweight universe, very little matter, and so the cannonball easily escapes its planet, or the universe easily escapes the gravitational pull and will expand forever. It has escape velocity. And so by measuring the slowing of the expansion, the deceleration over the last few billion years, we thought we could actually weigh the universe and figure out what the ultimate fate was. Now, it turns out we can make these measurements with supernovae. I told you earlier that they're great standard candles. It turns out not any kind of supernova will do. There's a very special class of supernova called the Type 1a supernova, and the famous Indian astrophysicist Chandrasekhar first showed in the 1930s why and how it's so special. It turns out that the core of an old star, it's called a white dwarf, can only exist at a mass up to about 1.4 times the mass of our sun. This is now known as the Chandrasekhar limit, because at that mass or lower, it can hold itself up against the crushing gravity that tries to compress it. But if you go just a little more massive than that, then you get a runaway thermonuclear explosion. It's like nature's own standard bomb. And so we believe that these white dwarfs live near other stars, and when mass transfers over, is pulled over, they reach this Chandrasekhar limit and explode. Well, that's fantastic for cosmologists because it's exactly what we need, an object that really is a standard candle, that everyone blows up at just about the same luminosity because it always blows up at this same critical mass. And they're also extremely luminous. They're as bright as 4 billion suns over the course of a few weeks. And so you could see them halfway across the universe or even further with the Hubble Space Telescope. Okay, so then we have to find these supernovae. And here are 4 supernovae from 1995 that we observed. You might wonder how it is that we actually find these. And I think you can see in the picture it's quite easy. It's just the bright spot at the end of the arrow no, we add the arrows later, I'm sorry. No, you're right, we actually do have to find the supernovae before we put the arrows. We've never seen the arrows in space. But nevertheless, we still have to find them. And how do we find them? Well, first you have to realize that a supernova is an extremely rare event. One blowing up in our galaxy, it won't happen only once a century, maybe only once every 2 centuries. So you're looking to sort of win the lottery when you find a supernova. That is, at one supernova per galaxy every 100 years, you would have to stare at one galaxy for about 100 years to find one. However, you quickly realize, right, that also means that there will be one supernova in 100 galaxies every year. So now pick your favorite 100 galaxies and stare at them. Now you're likely to win, and you can see where this is going, right? This is like winning the lottery by buying all the lottery tickets, right? It's very unlikely unless you have a scheme. And so in our case, we will take images that contain thousands or tens of thousands of galaxies, which guarantee that we will find a supernova every month when we want to find one, and so on. And then we enlist computers, and this was really a big development in the 1990s, was computers that were fast enough and detectors that were large enough, had enough pixels to cover the sky, and then computers are very good at matching two epochs of imaging separated by a month and letting us know when there's a new point of light, something that appeared that wasn't in the image a month earlier. So in the mid-1990s, we formed a team called the High-Z Supernova Team. We thought to measure the slowing of the expansion, the deceleration, and that this would tell us what the ultimate fate of the universe was. Now, I was very fortunate. It was around 1997. I was a postdoc, and I was picked to lead the analysis of one of our first large data sets. And so I had done a lot of steps to analyze the data, and it was getting to be that final step to sort of get to the answer. What is it? And I wrote a simple computer program that would relate the amount of slowing expansion seen from the supernovae and convert that to what the mass of the universe was, knowing that, whether that omega matter number is more or less than 1 is the whole ball game. It's the whole story of whether the universe will recollapse or not. Now, what I had failed to notice up until this point was that the deceleration of the universe on the left-hand side, that wasn't happening. I thought the universe would be decelerating and that would give you what the mass of the universe was. But here's this key page from my lab notebook here where I wrote the first answer of what is the mass of the universe, and instead of getting a number more or less than 1, I got a negative number. Now, that doesn't make any sense. There's no such thing as negative mass, but computers don't know physics. And so if you give a computer a really simple equation like this one, and then you give it some bad physics, like you make the left-hand side negative, it's going to make that equation be true by making the right-hand side negative. That is, computers don't know physics. And so I quickly realized, I just hadn't looked yet at the data, that the universe was not decelerating. The left-hand side was not positive, it was negative. This negative sign actually was telling me that the universe was accelerating and that there was something else going on. There's no such thing as negative matter. However, enter Einstein's Cosmological Constant, that could do the trick. That is something that can make the universe accelerate. It can make the equation actually be a negative number on the right-hand side. And so I spent a few days, a few weeks working on these results, checking them, and doing a calculation to figure out exactly how sure we were that this was true. And in the sort of way scientists look at things, we were 99.7% sure that this was not a fluke. And it was time to begin talking to my other colleagues on the team about how we would understand, explain, and talk about this. So it's really interesting. I share now the sort of email by email from my colleagues back and forth over the course of 24 hours after having first seen this result. So you could sort of see how scientists sort of react to these things. Very, worried, concerned that something is wrong, tend to be very conservative because it's very easy to make a mistake. So this was all on January 10th, 1998. Alex Filipenko, who's a professor in Berkeley, California that I was working with at the time, Adam showed me fantastic plots before he left for his wedding. Our data imply a non-zero cosmological constant. Who knows? This might be the right answer. Bruno Leibengut from Germany, also on our team, concerning a cosmological constant, I'd like to ask Adam or anybody else in the group if they feel prepared enough to defend the answer. There is no point in writing an article if we are not very sure we are getting the right answer. Brian Schmidt, my colleague in Australia, who had led the efforts to find the supernovae, wrote, I agree our data imply a cosmological constant, but how confident are we in this result? I find it very perplexing. Bob Kirshner, who was my thesis advisor at Harvard, he was on sabbatical in Santa Barbara at the time, wrote, I am worried. In your heart, you know the cosmological constant is wrong, though your head tells you that you don't care and you're just reporting the observations. It would be silly to say we must have a non-zero cosmological constant only to retract it next year. So he was sort of looking ahead at how foolish we would be. Mark Phillips from Chile, also a close collaborator on the team. As serious and responsible scientists, we all know that it is far too early to be reaching firm conclusions about the value of the cosmological constant. John Tonry, a colleague in Hawaii, who remembers the detection of the magnetic monopole and other gaffes? On the other hand, we should not be shy about getting our results out. Alex Filipenko responds, well, if we're wrong in the end, then so be it. At least we ran in the race. The race he was talking about was there was a competing team at the Lawrence Berkeley National Lab that was collecting their own data, observations of supernovae, and making exactly these kinds of measurements. We didn't know what they were getting, but we didn't want to be last in the race either. I got back from my wedding and quickly dashed off this email. The results are very surprising, shocking even. I have avoided telling anyone about them because I wanted to do some cross-checks. I have, and I wanted to get further into writing the results up. The data require a non-zero cosmological constant. Approach these results not with your heart or head, but with your eyes. We are observers after all. Alejandro Clociati in Chile responded, if Einstein made a mistake with the cosmological constant, why couldn't we? I was never clear whether that was supposed to be reassuring or, if you make the same mistakes that important people make, maybe you're important too. Nick Sunset from Chile wrote, I really encourage you, Adam, to work your butt off on this. We need to be careful. If you are really sure that the cosmological constant is not zero, my God, get it out. I mean this seriously. You probably never will have another scientific result that is more exciting come your way in your lifetime. And of course, Nick was right. So we went ahead and wrote this paper claiming that based on observations of supernovae, both far away and nearby, to tell us the past and present expansion rate of the universe, that it was accelerating and that this equated to the universe now being about 70% in the form of dark energy, or what Einstein would have called the cosmological constant. A competing team came up with a very similar result in a very similar time frame, and so this became the breakthrough of the year for Science magazine in 1998, with a picture of Einstein on the cover, that he would have been amazed. This thing that he had discovered as important and the way to solve a particular problem, and then that problem didn't exist, but that piece of physics never went away. So really the $64,000 question is, why is the universe accelerating? And we don't really know. I mean, this really is the big question in cosmology. We've been wrestling with it for a long time since then. I mean, we have ideas. Option number one is what physicists call vacuum energy, and Einstein would have called the cosmological constant. And it's based on two ideas, or two realities. One is in quantum mechanics that tells us that empty space still has energy in it, that you cannot get rid of that energy. And then an idea from general relativity that energy in empty space will have gravity that is repulsive. And so it sounds like the perfect marriage, but these two theories are not compatible, and that's evidenced by the fact that this calculation, the amount of vacuum energy that physicists expect, is about 120 orders of magnitude different than the one that actually works in general relativity. So we're really stumped there. Another possibility is that it's dynamical dark energy. So it's like this, but it's temporary. It's the energy from a field in space. Think of any field the electric field or the magnetic field. This would be a field, and it has energy associated with it, and that will temporarily look like vacuum energy, but it may change, it may decay, it may evolve. And so we hope to look for observational clues that distinguish these. The third possibility is actually a modification of gravity, that we are applying gravity on scales that nobody ever applied it before, and maybe something is breaking down in that. Now, I have to say, in around 1998 to 2000, we weren't thinking so much about these. We were just thinking, what if we're just wrong? What if we were fooled by the supernovae measurements to come to this conclusion? It's like when I showed you before, you can get fooled by a lighthouse if it's a foggy night. It would be something very similar. What if the distant supernovae looked distant because their dimness was really due to maybe there was a fog in the universe? What if between galaxies it was kind of a gray dust or fog? Could that be fooling us? Or what if the supernovae back then, because after all we're looking back in time, what if they were just born fainter, fooling us? So the idea here is, when we see a supernova looking faint, we thought that meant it was far away. But in reality, when we saw it faint, it was not that far away. We were just looking through maybe a whole lot of dust. So the community and we worried about this quite a bit. However, there was an important test to be done. if we could look at ever more distant supernovae, in this case, we would be looking through more and more of this fog, and so the effect would just amplify. Whereas if this was really due to dark energy, that effect is predicted to dissipate if you look far enough back in time, because when the universe was more compact, it would have felt its gravity much more strongly, and so it would have been pretty insensitive to this dark energy. So the idea was, if we could find more distant supernovae, further away than anybody had ever found them, then we could distinguish between these two possibilities. So how do you find something that's even fainter and further than ever before? Well, you need a very special telescope to do that. So let me just give you a quick primer on telescopes and their power. Here is the improvement over the eye of telescopes over the last 400 years. So Galileo got us the first jump of about a factor of 100 over the eye. And then telescopes gradually got more powerful as they got bigger, as they were put on mountaintops, as they had better detectors, going from your eye to photographs to electronic detectors. And then people had the bright idea to put a telescope in space, to put it above the blurring effects of the atmosphere, so that when you take an image of a galaxy plus its supernova far away, this is what it looks like with Hubble, and this is what it looks like with a large ground-based telescope. And so this gave us even more power. And then when the astronauts revisited the telescope, they would put even more powerful detectors in. So we really are capturing about a factor of 1 trillion over what the eye can see. So particularly in 2002 and 2009, the astronauts installed more powerful cameras in Hubble, and my colleagues and I used these cameras to find the most distant supernova explosions ever seen. And when we did that, we were able to test some of these other ideas that people had suggested, and we concluded that the supernovae were not fooling us, that we were actually seeing the universe accelerate. We could see it slowing, decelerating before it began accelerating, because the universe has gone through two periods. A period early on when it was dominated by the attractive gravity, and that's how structures formed in the universe, like galaxies. And now this current epoch where it's dominated by this dark energy that is pushing things apart faster and faster. So, of course, we never believe anything in science, generally, if we learn it only one way. We like a lot of cross-checks. We like a lot of independent ways to learn things. And so, like in the beginning of this talk, when I talked about the different ways you can measure distances, parallax and lighthouses and airplanes and things like that, just like that in cosmology, we have many ways to get to this same kind of information. And so just to very briefly run through those, the first was, of course, using supernovae in 1998 and seeing that the universe was accelerating and about 70% in the form of dark energy. A few years later, astronomers announced that they could see another effect, that when you looked at little bits of light, little photons of light from the very distant universe, as those photons fell into gravitational wells of clusters of galaxies, they gained energy, and they lose that energy when they climb back out. But dark energy pries apart those potentials. It actually starts to pull the galaxies out of them, and so they don't lose as much energy as they gain. This is called the integrated Sachs-Wolf effect, and this was shown to require 70% dark energy, just like this. Way number 3 was observations of the cosmic microwave background told us the total sum of all energy and matter in the universe, and when astronomers announced they found only 30% of that took the form of matter, that left 70% in the form of dark energy. Sounds familiar? A couple others, we see that the largest clusters of galaxies are no longer effective at pulling in new galaxies because of dark energy, and we've seen a change in the absolute scale of the universe over the 13 billion years that requires dark energy. But the way we were really sure that dark energy existed, or that the universe was accelerating, was because we won the Nobel Prize. And you don't get the Nobel Prize if you're wrong. So it must be true. And so when we went to Stockholm in 2011, they told us it was true, and we were happy about that. And we had a good time there as well. But there was kind of a dark side to all this enjoyment about the accelerating universe, which was well captured by this show called Big Bang Theory, you might be familiar with. Shortly after we received the Nobel Prize, they kind of made fun of us a little bit. Here's that section.
2 a.m. What are you doing up?
Nobel Prize acceptance ceremony streaming live from Stockholm.
Sure. I want to see what all the scientists are wearing this year.
Look at these men. They've managed to win the top science prize in the world with no more understanding of the quantum underpinnings of the expansion of the early universe than God gave a goose. You should...
Right, so that's exactly right, what he said. You know, we do not understand the quantum underpinnings of what he said, because you know, we have seen the phenomenon of acceleration. We have ideas about it, but you know, we have not understood at a very detailed level the physics of it. However, we have new tools over the last 10 years or so that have really been a big help in our quest to understand dark energy, at least the way I do it, through observations and measurements rather than theory, although there's people here who work on the theory part. Two I want to draw your attention to both happened in 2009, 10 years ago. The last upgrade of Hubble really upgraded it with a really fantastic camera, Wide Field Camera 3. Here are the astronauts putting that in. And the European Space Agency launched a new satellite to study the radiation left over from the Big Bang, called the cosmic microwave background. That was Planck. And the new camera on Hubble has allowed us to improve the present measurement of the expansion rate of the universe from an uncertainty of 10% before to about 1.9%. And meanwhile, Planck has given us higher resolution, higher precision measurements of the cosmic microwave background. It's the third satellite in a sort of series of generations to do this. However, as they say, be careful what you wish for, because we've learned some interesting things from this. One of the exciting things about the cosmic microwave background is it allows us to look at the story of the universe, the story of that cannonball that was fired, in a totally different way. See, before, when we were watching that cannonball with the supernovae, that was what the recent history was for that cannonball. We were looking at the last few billion years of its trajectory. But having this radiation from the Big Bang, seeing how cool it is sort of like being able to track that cannonball blast and predict it from a whole different kind of physics. Let's say, imagine you could look at the heat and the smoke and the cooling off of the cannon as a completely independent way of judging what's going to happen to that cannonball, right? Was it a big blast or a small blast? So in the cosmic microwave background, we are able to see that sort of equivalent of the cooling cannon. And in particular, we can actually measure spots that form in the image of the radiation from the Big Bang. Those spots are the size or distance that waves of sound or pressure waves can travel before the universe becomes transparent, before that radiation can first get out, about 300,000 years after the Big Bang. And so these become characteristic spots that we can still see today in the collections of galaxies around us. So what I'm presenting to you is instead of starting from the present and looking back in time, with the cosmic microwave background, we could start from the beginning and look forward in time. Two different ends to learn, hopefully, the same thing. And that's where things get interesting. As I described to you, we have an understanding of the universe as being about a third dark matter, about 2/3 dark energy, a few percent of atoms, and it gives rise to this expansion history of the universe, which presently is accelerating because it's dominated by dark energy. In the past, it was decelerating when it was dominated by dark matter, and we have a very precise measurement of how fast the universe is expanding today based on the kind of measurements I've been telling you about. And that also tells us, if we take this back in time, that the universe started about 13 billion years ago. However, if we use this other kind of information that comes from this afterglow of the Big Bang, then we get a very similar story for the universe. The shapes of these curves, these two eras are there, except we get a prediction that the universe should be expanding today quite a bit slower than what we actually observe, about 9% slower. And at this point, it's about 5 times the error bars of these. And also, that story has the universe starting about 1 billion years earlier than this other story. So they're two parallel stories, but they're just a little different from each other. So it really raises this question, how old is the universe? Because if we can't distinguish between these, we're not quite sure. But more importantly, what are we missing still? What are we missing in this description of the universe that means that when you start at two ends of cosmic time, you don't get quite the same answer? So to sort of wrap this up, on the one hand, you could see the story of cosmology in the last 20 years as a sort of glasses half full story. We have finally learned what the universe is made of. We have a standard model of cosmology, like the particle physicists have a standard model of particle physics. We call it lambda CDM, and we have figured out, for the most part, what the universe is made of. However, the glasses half empty part points out that 95% of the universe is in these dark forms, dark matter and dark energy, whose microphysics we don't really understand. And then we see some strange tensions in this story, like the fact that when we start at two ends of cosmic history, we get this different answer. This might be evidence of something else going on. It may help teach us that dark matter and dark energy are a little weirder than we are assuming in the standard model of cosmology. So these are really exciting times, and as usual, more data is needed to understand this better. But more data is on the way. Both the European Space Agency and NASA are planning space missions. They kind of look like Hubble Space Telescopes, but they're dedicated to studying dark energy. ESA is launching Euclid, and NASA plans to launch W first. And the goal of these telescopes will be to tell us which of those three options I described for dark energy is what dark energy actually looks like. So I'm going to finally end this talk with a sort of plea or telling you why I think it's so important to study dark energy. First of all, it is most of the universe. We can't really claim we understand the universe when the biggest piece remains so mysterious to us. Because dark energy is dominant today and is driving the expansion of the universe, it's very difficult to say what the fate and even origin is of the universe until we understand dark energy better. But I think the real reason that we're most driven to understand dark energy is understanding it really lies sort of at the nexus of our two most successful theories of physics, quantum mechanics and general relativity, but two theories which are incompatible. And sometimes when you're stuck and you don't know how nature manages to make those two theories compatible, it's nice to have a clue, to actually look in the back of the books, as they say, and see how does nature actually do it. And dark energy seems to be the best example of that. We get to watch how the universe uses or employs or works with dark energy, and we think that might lead to a clue that helps us understand physics a little bit better. So I will end there, and I'm happy to take any questions that you have.
Well, thank you very much for a fantastic lecture. Questions or comments? No.
What was so good about the cameras that were put on the Hubble that made it perform so much better?
A couple of properties that make them better. Their quantum efficiency was better. So the early generation, 10% of photons, maybe 20% of photons that hit the detector were captured and 80% would bounce off. We're getting up to 90 or 95% quantum efficiency on these. Also, the pixels are smaller, which means you get better resolution. We used to not be able to make detectors with that many pixels and talk to all of them. And so we have just much better detectors from that standpoint.
Two questions. One a fun question, one a more serious question. The fun question, so look, astronomers have messed this up twice. Astronomers made the story more complicated twice. Once they told Einstein that the Hubble constant was 500, and that led to the Big Bang, to the steady state theory and all that kind of stuff that took a while to die down. And then the astronomers told Einstein that the universe was not expanding. So once again, that led to all kinds of troubles. So what is it now that we astronomers are telling the theorists that's simply wrong? So that's a serious question. The fun question...
Wait, that was a fun one or that was a serious one?
Yeah. Why didn't you mention Cepheids, the contribution? Why didn't you mention Cepheids?
Why didn't I mention Cepheids? Yeah, I will in my technical talk tomorrow. I'll talk quite a bit about Cepheids. So Cepheids are pulsating stars. They are also standard candles, and they are used to connect these very distant supernovae to geometric methods like parallax. And so that's something that, as I said, I will talk about tomorrow. Let's see, the answer to the question of why do we get stuff wrong sometimes, and doesn't that have ramifications? It does, but I guess I would say on whole, we end up doing more good than harm. I mean, that we still end up learning things, but you're right. I mean, if people would just patiently sit there and wait and give us, many hundreds of years to get it all right and come back then, we'll tell you the final draft. But, you do get to see our rough drafts along the way.
Given that there's this dramatic difference, and we've previously assumed from a cosmological perspective that there are attributes of the universe that were static when they weren't, is it possible that dark matter, dark energy, etc., are in and of themselves not constant factors,
right.
i.e. that they might be produced, dissipated, etc., and that's leading to these effects? Great question.
Like and this ties to your question. We've had ether, we've had epicycles, we've had things that weren't true. So can we derive from that all things today aren't true as well? And I would say no. I would say sure. We get things wrong sometimes, and I'd be crazy to tell you I'm absolutely sure dark energy and dark matter are exactly like this. I mean, you always have to keep your mind open to something else. So if you remember option 3 on my list, I didn't say explicitly. I said that we don't have the right theory of gravity, but what comes along with that is, and then there's no dark matter perhaps, and then there's no dark energy perhaps. So if somebody comes out with a new theory of gravity and it does away with dark matter and it does away with dark energy, but it explains everything else and it works and it fits the solar system and all that good stuff, then we would embrace that, no question. But that has never happened before, whereas general relativity seems very successful in every realm in which we test it. And why should we be so surprised that things are dark? I mean, it's almost a human bias to believe that everything should be visible to us. I mean, that we are somehow the most important creatures in the universe. If they don't announce themselves to us, then maybe they don't even exist. But, the reality is that, our way of seeing things, of collecting photons over a very narrow range of wavelength, it just works for us, but does not have to be the way the rest of the universe is. So I just think we need to be open to that reality.
From a novice point of view here, how does Kip Thorne and his colleagues' work with the discovery of gravitational waves affect your work?
Right. So gravitational waves, which are also showing us things in the dark. So for example, 2 black holes spiral together, they don't emit any light, and so you wouldn't see them, but they do create these tiny ripples in space called gravitational waves, which have been now detected. And it's giving us a new window on the universe where we could see dark things moving in space. In my work, it's particularly interesting because they're offering another way to measure distances. Theirs is a standard candle as well. It's just not a standard candle in light, it's a standard candle in gravitational waves. And so that looks very exciting, very interesting, and they promise over the next few years to be able to weigh in on some of these questions.
Actually, it's a comment rather than a question to add to your quotes. So when your paper came out, I was a PhD student with Stephen Hawking, and soon after it came out, people came over from the Institute of Astronomy in Cambridge to give a talk about this. And then we went back to his office afterwards, and we said, well, what do you think? And, of course, he was very, very slow in typing, and then he says, it's wrong. The cosmological constant is obviously 0. Theory is much more reliable than observations. And then, of course, he kind of proceeded to be a little bit more reasonable because you've already referred to the fact that, there were the Hubble wars. And in fact, in the Institute of Astronomy at that time, there were multiple camps, discussing the value of the Hubble constant, where they were sort of, factors apart from each other. But it was just, the absolute clarity that, theorists are much more reliable than observation. He has a very famous paper, a pretty well-known paper, with the title, I think, is something like "The Cosmological Constant is 0."
Right.
So
there's this. I see this a lot, particularly from, I got to say, from older generation mostly, where they go, well, I've seen things be wrong before, so I'm going to be kind of smarter than everybody and recognize everything's wrong. And, those people are right 95% of the time. I mean, they're definitely playing the right odds, but there's something kind of cynical about it too, because if you conclude everything is wrong because you're playing the odds, you'll never discover anything. I mean, and so you just have to think critically about each of these things as they come along. You can't just use blanket rules and say everything's wrong.
Okay, any further question or comment?
For those who believe in multiple universes, do they believe that all of these universes are expanding also?
I don't know. We'd have to find some of them and ask them. But I know it's a natural extension of some theories that there are multiple universes, and all the other universes presumably would obey the same set of physics that tells us that the universe can be contracting, it can be expanding. It depends on what that universe is composed of. I mean, they could have a vanishing amount of dark energy and have lots more dark matter. It would depend. And so, unless somebody's theory actually gave sort of odds for what these distributions would look like, it would be hard to say. It's very speculative, that whole subject of other universes, because it's not something we could observe directly. Yeah.
I guess my question is, I was always confused with dark energy because space is expanding, but my house isn't getting any bigger,
right,
and the solar system and everything.
I know, it's not very useful, is it?
Just between the galaxies. So,
yes,
how do you explain that?
Yeah.
Because
so it's it's the fact that when things are very compact, like your house or the solar system, then they feel their gravitational pull much more than this dark energy. It's a little bit like my rising loaf of raisin bread, right? The raisins aren't also growing with the loaf, right? They are held together by that strong skin. And in this case, the gravitational, what we call binding force of gravitationally bound objects that are smaller, they don't notice. They are barely affected. It's very weak, this dark energy. It's that when you get into deep space where you're between galaxies and the densities of matter is very low, then this sort of background thing can overcome.
Yes. You mentioned we don't have a very good understanding of dark energy and dark matter, but there's one other feature of the universe that we don't understand, at least as far as I understand it, and that is Alan Gut's theory of inflation. Do we have any understanding of what caused inflation?
Well, one of the interesting things about inflation is dark energy. I mean, this mechanism that I'm talking about is exactly how inflation operates. It's a period shortly after the Big Bang where we think that there was a field in space whose potential energy was like vacuum energy, and it drove the expansion really fast. So in a way, there's a connection between the things that we don't know, which makes physicists want to often look for the broad answer to all of them. So far as I know, I haven't heard anything really compelling about that connection. And so, what gives rise to inflation, what that field is exactly, I think is still not that well known. It's a mechanism, but, like the current acceleration, we don't know at a very detailed level why it had to happen.
Okay, well, I think we can wrap it up now. Thank you very much for a wonderful talk.